Okay, so what we're going to look into is your what is actually climbing flight, and then what is the performance that you expect if your aircraft is actually start to climb, and then obviously what happens if you then, for example, like remove one of the components of your thrust, for example, one of the component of your forces acting on your aircraft. In this case, for example, is very easy to remove the thrust is by switching off your engine, for example, and then obviously then will make your aircraft start to glide, right? So how do you actually look into the aircraft in performance? So obviously we will look into the equation of motions. Alex says the code is not on. Well, I'll double check. It's 8491. I think that's the one that I 8491. Yes. I think that's the 8491. Right. So it works okay now, Alex. If you look at the equation of motion again, we always start with the Newton second law, which is obviously sigma force is equal to acceleration mass time acceleration. In this case, let's write it as dv dt. Then sigma force, if you look at the stability axis or wind axis, which is in this direction, this is your x stability, or sometimes because it is actually aligned with the wind in coming to your aircraft. Sometimes it's also x subscribe with a subscript w, and obviously this is your z in that direction is your zs. Then in x s, your sigma force is basically thrust minus drag, right? So that's what actually is there. And obviously there is another component, which is obviously if this is gamma, right? So then there's a component of your weight in this axis, and of course there will be another one in that one. So this one is obviously w sine gamma, but that one is obviously your w cos gamma. So if you look at only the x-axis, then that's what you get, right? So that is the m dv dt, thrust minus drag minus, because it's also opposite to the thrust, and minus w sine gamma. And this one, if you look at in z-axis, so obviously you know that the angular rate is your speed divided by radius, and then the m phi d gamma dt is obviously the speed because of the rotation of gamma multiplied by v, and then the component, the sigma f in the in the z-axis component is obviously the lift minus the omega cos gamma there. So there's only two components in that direction, right? So, but bear in mind, you have also another motion components. This is a force component, obviously equilibrium of forces, but you have also the motion components, in this case, your velocity, right? So if I draw that, the velocity is over there, but if I draw that starting from here, for example, so this is not force, but this is the velocity, vector velocity, then obviously you have two components in this axis, which is your horizontal artificial horizon axis, then this is what we call it v horizontal, right? And then you have also your vertical velocity there, which is vv, vh, and obviously this is gamma, then vh is obviously v cos gamma, and then your vertical velocity, which is then your dh dt, right, which is also your rate of climb, because changes in altitude over time is your rate of climb, which is your v sine gamma, the component of this one. You follow? So that is our ammunition to look into the climb performance in this case. Right. So this all those equations are then write again in this. So you have this. Well, let's see. This is the first equations. This is the second. This is the third, and this is the fourth equation. So you have this from the x-axis equilibrium, right? Remember that. So t minus d minus w sine gamma divided by m, because obviously in the initial equations m is just there. The same as this one in z-axis, which is d gamma dt mv. Then I move it over here. So L minus w cos gamma. Then this is the component in horizontal, the velocity in horizontal. And then this is the component velocity and vertical, which is obviously this also equals as your rate of climb. Okay, so now rate of climb, we know that rate of climb is something that you want to find out if you want to check the performance of your aircraft. So what is your rate of climb? I think in military aircraft, in fighter aircraft, rate of climb is very important. That actually indicates your air superiority or indicates your maneuverability. It also indicates your agility. But in our commercial jet, passenger jet aircraft, actually rate of climb is not something that you want to really to make it like you want to beat your enemy in terms of rate of climb. But actually rate of climb, usually the objective to design the aircraft is just to make rate of climb as at optimum as possible in order to have a good to achieve a good performance. But at the same time, you don't want that rate of climb will upset the passengers. For example, if you have like rate of climbs 25 meters per second, I think that's almost quite quite abrupt for the passengers to experience. So normally the standard rate of climb for passenger aircraft, it's usually measured in feet per minute, is between 1,500 to 2,000 feet per minute. That's is for commercial passengers aircraft, right? But of course, for a military aircraft, you want that as high as possible, and then you don't really care about how much fuel that you burn by your engine if you want to achieve the rate of climb as high as possible. Okay, so let's go back to the equation. This is obviously the second equations that you look at before. So W is obviously initially is in this side, but then I move it over there, and T minus D minus M dV dt. So if you look at back, if I just switch back, so this is the equations that we looked at, right? So you know that sine gamma is over there together with W, but obviously if you put that sine W sine gamma to the other side and then dV dt to the other side, then you will end up with this equation. Now, obviously, if you make the gamma as a single terms, then you got the arccosine of whatever inside of that bracket, which is obviously the one there on the top there. Now, if the airspeed is constant, remember, I always say that bear in mind if you read the exam questions, for example, if it says steady climb, which we're going to look at that in next slide anyway. When we say steady climb, steady means there's no accelerations, right? So there's no acceleration, meaning that this equals to 0. Okay, so if this equals to 0, then you have only the terms t minus t divided by w, which is that one over there. So then gamma, which is your climb or flight path angle or climb angle in this case, then is only arccosine of t minus t divided by w. Okay, now this is quite well, there's a few information that you could gather from this statement here. Is it means that your thrust should be greater than the drag, otherwise you will not get gamma. In case, for example, t equals d, right? Meaning that thrust equals to drag. That is what happening in steady level flight, right? So in our climbing case, then if you want your aircraft to climb, then your thrust should be at least bigger than d. So that becomes something divided by w, and you got your gamma there. If t equals d, obviously this becomes 0, then your gamma will not be possible or will not exist. So there will be no climb, okay? And then obviously if there will be no climb, it means that your aircraft is only in steady level flight, like what we discussed last week. Okay, so remember that. So the aircraft gains altitude if there is an excess of thrust, meaning that t minus t should be greater than 0. Okay, if t minus t equals 0, is steady level flight. If t minus t less than 0, your aircraft, instead of climb, it will descend, right? So that is when we say, when you switch off your engine, meaning that you don't have any t in there, then you have only minus t divided by w, then your aircraft descending instead of climbing, okay? Right, so now, if you look at the equation again, your, for example, like for the climb angle equations from previous slides, sine gamma is equals to t minus t divided by w. Now, you can see here that if I manipulate slightly the equations by taking the w here as equals to L, which I assume that the flight path angle is kind of like small. So cos gamma equals 1, then L equals W, and I could replace this W with the L. Now this becomes the one that you have seen before in steady level flight, that sine gamma is equals t minus t divided by W minus 1 over CLCD. Okay, it can be seen here that you can, if you want to achieve this one as minimum as possible, right, then you could get this as maximum as possible. Then returns again to your CLCD performance of your aircraft, which is your well, CLCD, it's your aerodynamic efficiency. Okay, we have already discussed about that a few times now. So if you want that for small angles, the maximum climb angles, which is obviously corresponding to your rate of climb, will be will happens if this obviously at maximum efficiency, when you climb at maximum efficiency, aerodynamic efficiency of your aircraft. Okay, so if we go back to the statement of rate of climb, which is V horizontal, sorry, V vertical, not V horizontal, which is your V sine gamma, sorry, V sine gamma, right? Then the sine gamma you replace with this, then you got this V at lift to drag maximums multiplied by gamma maximum. In this case, again, we assume that gamma is quite small. So if we go back again to what we agreed before, if you take into account a small angle, so the cos small angles will be equals to 1, and then the sine of small angles will be equals to the angle itself, which is gamma. So that's why then rate of climb here for a maximum happens when you take the v, the velocity of your aircraft at lift to drag maximums multiplied by your gamma maximum. Okay, right. So now the question is how you conduct or how you perform your climb. There are two types of climb. Obviously, we have already discussed about that. The first one is what we call it steady climb, where dv dt equals 0, which is there's no acceleration. So we look at that as steady climb. Then obviously constant speed or steady climb, which is dv dt equals 0. Then the second one is when you try to make your aircraft climb with a constant angle of attack, which is called as quasi-steady climb, quasi or quasi, or usually I call it quasi-steady climb. That's a British term of that. Quasi-steady is a prefix, quasi as a prefix, so you have to say it as quasi-steady climb. And of course, the third one, now this is related perhaps with the fighter I mentioned, because if you climb with a commercial passenger aircraft, the maximum, as I said, in order not to upset your passenger, is about 2,000 feet per minute climb rate, the rate of climb. Then that will not really happen significantly in terms of Mach number change. But if you are talking about the fighter, obviously the climb rate is so high, then the change of Mach number will be quite significant. Then you could do this the third constant Mach climb change. But we're going to have a look at that anyway. So what happened if we look into the first one, but we have already looked at the first one already by looking into the flight path angle, the climb angle. But here, obviously, back to the original statement of lift, which is lift equals half rho v square s cl. Then obviously the v that you need in order to climb is 2 divided by w over s divided again square root of 2 times w over s divided by rho cl. Now I have already introduced you with this term, which is the wing loading in your aircraft design. This is quite important in terms of design. So in this case, if you want to have the climb performance good, or you want that big, then you want that wing loading is also big. So if you want the wing loading is big, then for a given value of weight of your aircraft, then you want to make this as small as possible, right? So wing loading will decrease. Wing loading will increase if s going down. Is that right? At any particular given w or any particular given weight of your aircraft, right? That's why in your constraint analysis, you want to have your thrust to weight ratio going down, but you want your w over s going up, as high as possible, but obviously within your design space. Now, for the power, we talked already about what is actually the power. The power is obviously your thrust multiplied by your velocity. So if you multiply your thrust with the velocity, you got your power. Then obviously from the previous equations, that equals to drag multiplied by your velocity, and then your weight component multiplied by velocity. Then obviously this, which is initially is only m dv dt, will become mv dv dt. Right. So that is the necessary power if you want to climb with a certain angle of gamma. Right. So we have a look at this already about the steady climb, rate of climb during steady climb, which is dh dt, which is simply is v sine gamma, the vertical component of your velocity, then which is equal to v sine v times t t minus t divided by w, and then if you know this as power, t multiplied by v is power, then it's power minus dv will drag multiplied by velocity divided by weight, right? So this is, we call it excess power, because you have to have an excess power in order to gain rate of climb or to climb. And then sometimes if you divided this excess power, which is your power available minus the drag, power by drag divided by W. Sometimes if you look at different literatures, this is called specific excess power. Right, so don't get confused with that. Excess power is this, but because you divide it by W, your weight, then it becomes specific excess power. Now you can actually notify from these equations during the climb. Obviously, rho gets lower, and the airspeed is not constant anymore. That's true fact from atmospheric layer. Obviously, in order to achieve a steepest climb and maximum climb angle, the aircraft must accelerate and use its excess power. That's why it's in order to get this quite constant, because of the rho basically will get lower and lower and lower when you climb your aircraft. Then that makes your airspeed obviously also become need to be increased, because rho is decreased. Then rho, if you want to have a steady climb, then a v has to increase all the time to compensate that rho is decreasing, right? How you make the v increase all the time? Obviously, you must accelerate by putting it your engine with the access to keep the excess power is always positive. That's why sometimes people say that the steady climb is very difficult to achieve because then you have to adjust your thrust accordingly, where to make the V is always always big, always increase in order to have excess power, in order to have a positive rate of climb. Okay, but it will really this assumption is slightly quite unachievable or overestimate, because usually in order to do that, then your aircraft has to have an acceleration. But when we say steady, we always say zero acceleration. But because of this fact, then it's quite difficult to achieve. Then comes to the second mode of climb, which is what we call it quasi-steady climb. Now here, the quasi-steady climb is use the full equation of motion that we already derived early on, which is when we say, I think if I just write this here, sine gamma equals, what is it, the sigma f, which is t minus d minus m dv dt divided by w, right? So if I just put them together, like t minus d divided by w, and I for this term, and then obviously minus m divided by w is g, right? And dv dt, right? So I hope you know how I get that g, which is g is actually W divided by M, so M divided by W is 1 over G, right? So we know that V equals sine gamma, rate of climb is equals V sine gamma. Then if I take this as a sine gamma and I substitute to there, which is then you have rate of climb is equals V multiplied by whatever you have in there, which is T minus D divided by W minus 1 over G dV dt, right? I hope that I have enough space to work there to write further. But if you then you rearrange this, then you will have, I think I'll just use my, if I could just change slightly to my whiteboard, maybe it's better to use the whiteboard. So if I could just go back to what I write before, which is rate of climb equals, what did I, well, a V T minus D divided by W. And then if I put V, then multiply to the second term, which is V divided by G dV dt, right? So if I then manipulate this, if I manipulate that dV dt is actually dV dH times dH dt. You agree? Right? So then I could rewrite that rate of climb is equals V T minus divided by V G dV dH dt. You agree? So because a rate of climb, as we know, is also dH dt, right? Then if I move this over this term to the left side, so I have dH dt 1 plus V G dV, dV dH equals V T minus D divided by W. Okay, so then obviously if I just make this as a single, then I have whatever on top of that, which is T minus D divided by W divided by 1 over V G dV dH. Now, this is what you look at. Well, obviously, this is obviously rate of climb, right? dH dt is your rate of climb. So that's how that equation becomes access from the this. So if you look at that, this is exactly what I wrote before, what I derived early on, right? Now you can see the conditions that we try to achieve in steady level flight. We mentioned that it was not really possible because obviously V the speed, the velocity changes over the altitude because of the rho is changing. So that represented by this term, which is the dvdh, meaning that the change of velocity due to the change of altitude. That's how you look at it, look at it in physical meaning of that. Okay, so in order to climb using a quasi-steady climb mode, then your rate of climb is not simply just this, but it has to be this divided by whatever you have in this term. Okay, so that is the quasi-steady climb, rate of climb for a quasi-steady climb. Okay, now I mentioned in that actually the rate of climb in this case then will be affected by a lot of other terms or a lot of other parameters. First of all, I mentioned about thrust, right? So if you don't have thrust or your thrust equals to drag, then you obviously there will be no rate of climb, and then you just steady level flight, right? And of course, we look into the wing loading already, that W over S. Okay, your weight of your aircraft is also playing an important role in this, and obviously your drag as well, right? So if you try to draw your hodograph, hodograph means like the x-axis is your horizontal speed, and then your vertical axis or y-axis is your vertical speed, which is also your rate of climb. So this is the speed in horizontal, and then this is the speed in vertical. You then could draw a hodograph. I hope when you do your flight test, you could kind of like draw a slightly, assuming that you could fly in angle of attack constant. Then a typical hodograph is usually it looks like that. Right? This is the same as a graph or a chart that you have seen last week when we draw the power versus the velocity, or thrust versus velocity chart. But it's slightly upside down chart, right? So that is represent now, because this is a component in the x-axis, is your v horizontal speed, and then the y-axis is your vertical speed. Then obviously that you could represent for any point that you have here. This is your vertical speed. This is your horizontal speed, right? And this is obviously your gamma, your pattern, the climb angle, sorry. And then if you up to here, then you have your own other horizontal speed and vertical speed, but that you can see this is where you achieve your maximum rate of climb, right? So that is the maximum, and that is your gamma at maximum rate of climb. So gamma when rate of climb maximums. Okay, now when you take a slope touching that curve, that is where you have your maximum climb angle. I hope you understand the difference between this and this. Well, this is where you have your rate of climb maximum, which is that point there, which is point, say, point A. And then this, when you have your maximum gamma, which is this point there, which is when you touch the slope touching the curve, which is point B there. Okay. Now, why I want to show you this graph is basically back to the original statement. I said that hodograph is actually changing if your thrust to weight ratio changes. You see that there's a different hodograph for different values of thrust to weight ratio. This hodograph changes with the change of your aircraft weight. This hodograph, you could see that the bigger the wing loading, then you got your the smaller wing loading, because we want in design we want the wing loading as big as possible. So if you decrease the wing loading, then your hodograph is actually kind of like dropping down like that. If you have like a wing loading high, it will have a proper hodograph like that. But if you have like wing loading smaller, for example, then your hodograph is slightly dropped. Then obviously that affects your rate of climb, right? So because we talk about the gamma rate of climb maximum and gamma maximum in there. Now, this is the effect of your CD naught, which is your parasite drag or profile drag. So the bigger the drag, then also dropping your hodograph as well, then that will affect your climb performance. So the bigger the CD, the parasite drag, then dropping your hodograph down, which is obviously will drop your gamma. Well, first of all, will drop your rate of climb maximum, and as well as also will drop your gamma maximum, the steepest angles for your climb. Okay. Now the third one is climb with a constant Mach, because we know that for an aircraft, well, constant Mach happens accounts for velocity variation due to atmospheric density as well. So we can assume that we could do the climb with a constant speed if the Mach number below 0.3, but once you already fly with a greater than the Mach number greater than 0.3, then you have to consider the rate of climb will be affected by the variation of the temperature, because Mach number is a function of temperature. Then the variation of change of temperature due to the change of altitude will have to be taken into account with that. Now, how you get these equations is very simple, the same as the one that we have before, which is the equation when, you know, the one with the quasi steady climb, which rate of climbs is equal v t minus d divided by w divided by 1 plus v divided by g dv dh, right? Now, the change of velocity is equal to the change of Mach number, but the change of Mach number is affected by the change of temperature due to the change of altitude. Then if you use this fact that Mach number is actually your speed divided by speed of sound, where the speed of sound is k a square equals k RTs. I hope you know this individually. This is specific heat, the ratio of specific heat, which is for air is 1.4. I guess if you remember in thermodynamics, R is your real gas constants for air is about 207 something. I don't know what the unit is, like joule divided by meter square divided by Kelvin, something like that. So then if you use these equations there, the statements here, into the one that we already derived before, and then you will get this equation over there, which is the rate of climb is affected by the Mach number and the change of temperature due to the change of altitude. Okay, and of course there's like a constant here, which is your specific fuel, ratio of specific heat, which is 1.4. I think in some literature in thermodynamics it's equals to gamma, right? So for air is 1.4 or something. Well, 1.4. Right. So now the maximum climb angle. Obviously, you can see that it's affected by the excess thrust or excess power. In this case, we talk about excess power. But for propeller aircraft, usually the excess power have to be considered. You know, you have to consider also the efficiency of your propeller, which is sometimes represented by nu there, which is the constant propeller efficiency. I don't think there is a very good turboprop engine at the moment where efficiency equals to 1. Sometimes it's between 0.8 or 0.7. Sometimes the best is, I think, 0.9 or something. But anyway, the power that you give from your engine turboprop, which is the rotation of your shaft, the engine soft in your engine, then converted into the thrust to produce the thrust by your propeller. There will be some loss in there, which is compensated by the efficiency factor there, which is the is it eta? The Greek symbols eta. Okay. Right, so what about glide then? Well, glide is simply making your thrust equal to 0, then your equations before becomes simply like that. Then if you look at that, which is equal 0, then this is obviously, you don't need to consider that because it's going to be 0 anyway. Then you have only look into the first, the upstairs of those equations. Now you have simply that lead that is only sine gamma is simply well, you divided the second with the first equation becomes sine gamma over cos gamma, which is then tangent gamma. Tangent gamma becomes 1 over L divided by D. Again, this is your aerodynamic efficiency, right? What happened here is if you want your aircraft glide with a very good performance, it means that you have to have this as good as possible, or the maximum as possible, lift to drag maximum as possible. Okay, so so the minimum glide angle, I hope you understand what the minimum is. The minimum is obviously the glide angle is this one, right? So the minimum is as big as possible towards that direction. So if you want to have that glide angle as maximum, well, as minimum as possible, we're talking about negative value here, as minimum as possible, then you have to have your lift to drag, well, aerodynamic efficiency at maximum. Okay, in that case, then you will have the longer distance of delta x with a given amount of the altitude drop in here, or altitude loss. Okay, so if, for example, if you do this in your what is it called, the flight sim simulation later on, then when you try to investigate your glide performance, normally we fly with a different gamma. Then after you achieve a certain gamma, you will see that dx will no longer, well, you will have a certain gamma with a certain dx. For example, if you drop from 20,000 feet to 10,000 feet, so you drop about 10,000 feet, right? So delta H is 10,000 feet. And then with a different gamma, you varies the gamma, then you will see that dx will varies as well. But there is a chance when after you achieve a certain gamma that dx becomes much shorter than another variation of gamma. Then if you draw that into a hodograph, then you will see that is your maximum glide angle, in this case gamma. Okay, so I will talk about this in the tutorials sessions this week as well, just to give you some idea with exercise equations, exercise questions, sorry. Please have a look at that tutorial slides before you go to this tutorial session. So you see actually there's some questions that you might want to exercise yourself to answer that before we discuss that in the session. Okay, now go back to the rate of this, well, rate of climb. Then in this case, because we are descending, then rate of descent or sink rate, then using the same equations, like rate of descent is actually the component velocity, the velocity component in vertical, which is v sine gamma. And then simply is from there, you will see that, well, from the equation where t disappeared, your thrust disappeared, and you only end up with this. Then you have this minus v multiplied by d over L. Now you know that L is actually, well, v is actually square root of 2 times the weight divided by rho as CL, which is rho here is rho at your altitude, because there is also a density ratio there. So you see that rate of descent is basically, if I take this out, because this is under the square root, if I take this out and then combine it together with the CL, then you have that CL to the factor of 3 divided by 2. Then you see that the rate of descent depends on the weight, right? It depends on the altitude as well, because you have the rho there, but more importantly, it depends on this, which is CD divided by CL to the factor of 3 to the power of 2. So if you want that as minimum, right, again, the same things that you want to have that also, well, you want to have that minimum as well. In this case, the same condition for minimum required power in level flight. When you want to have that maximum, or sorry, minimum, then you want to have that this also minimum, or you want to have this maximum, you want to have that L over D is also maximum as well. Okay, you follow? So I hope that is actually the end of our lecture today. If you have any questions, you can ask now, or otherwise you can hold it until the tutorial sessions where we could discuss this a bit further in the class. Any questions? I hope you understand how all the equations, especially the one that I talked before, how you come up with this equation, rate of climb. I think I used my whiteboard because you can watch again this video and see how actually that statement is derived, the equation is derived, and then you can combine that with this, whatever I wrote that on the slide there, which is end up with this equation here. So I'm going to stop the